Venus is the brightest betrayal in the night sky. It looks calm, almost gentle, but it is the one planet that repeatedly proved something uncomfortable. The universe does not reward the closest target. It rewards the survivable one. For a brief window, we didn't treat Venus like a monster. We treated it like a destination. Then we learned what it really is, and the attention moved elsewhere. Here's the part most people don't realize. The United States has not flown a dedicated NASA spacecraft to Venus in more than 30 years. And the last time NASA put a probe into orbit around Venus, the year was 1989. That doesn't mean Venus stopped mattering. It means Venus stopped fitting the way we like to explore. Because Venus is the planet that punishes shortcuts. It punishes optimism. It punishes hardware. So the question isn't why didn't we go? We did. The real question is why we didn't stay. Why we didn't return at the same pace we returned to Mars. And once you follow the chain of reasons, you end up in a deeper mystery. Venus may be the most important planet for understanding habitability, including Earth's habitability. And yet it became the planet we learned to avoid. If you want the turning point, it has a name: Magellan. Magellan wasn't born from a clean, confident plan. It was built from what was available. Its radar system came from Voyager. Its propulsion module came from Mariner. Its star scanner came from Galileo. A patchwork mission assembled under pressure that ended up rewriting our picture of Venus. After a 15-month cruise, Magellan entered orbit around Venus in August of 1990. And for 4 years, it did something no camera could do. It used synthetic aperture radar to pierce the clouds and draw the surface in detail. Magellan mapped the surface at about 300 feet per pixel. It covered more than 98% of the planet. What it showed was not a quiet world. Venus looked paved in lava, shield volcanoes, massive and broad, lava plains stretching for thousands of miles, odd pancake domes, thick lava that spread out like syrup and froze into flat-topped disks, and coronae, ring-like features tied to heat rising from deep below the crust. Then came the clue that still makes researchers pause. Venus appears young, not like a newborn planet, young like a planet that got wiped clean. There are fewer than 1,000 impact craters across the entire surface. Earth's moon has millions. Mars has hundreds of thousands. A crater count so low suggests a major resurfacing event in the past few 100 million years. The surface may have been renewed on a massive scale, volcanism as a reset button. And that's where Venus stops behaving the way we expect. Without plate tectonics like Earth and with little to no water to lubricate crustal motion, Venus should have cooled into a stagnant, geologically quiet world billions of years ago. But Magellan's maps hinted at the opposite. Relatively recent volcanism and possibly volcanism still happening. The tesserae are a key part of this history. They're continent-like highlands, fractured, folded, heavily deformed terrain that stands above volcanic plains. Some scientists suspect tesserae are ancient crust, the oldest surviving rock on Venus, the leftovers from whatever Venus was before the resurfacing. If that's true, tesserae might preserve the most valuable evidence on the planet, clues about Venus's earliest climate and whether liquid water ever persisted long-term. But radar alone can only take you so far. Magellan gave us a global map, not a chemical fingerprint. It couldn't tell us what those rocks are actually made of. Magellan operated until October of 1994. At the end, it was commanded to dip into the atmosphere, and it burned up, swallowed by the clouds. Then the rhythm stopped. After Magellan, the U.S. did not continue with a steady, dedicated pipeline back to Venus. Part of the reason is momentum. In August of 1996, scientists announced something that hit the public like electricity: possible microscopic fossils inside a Martian meteorite called ALH 84001. That rock had been recovered in Antarctica in 1984, and it was thought to have been blasted off Mars millions of years ago. The claim didn't survive the way the headlines did. Later analysis showed non-biological explanations could produce similar structures, but the narrative had already done its job. Mars became the planet with a storyline, a place where life might have been, a place where we could land and keep operating. Then came the long parade of missions: Mars Pathfinder and Sojourner in 1997, Mars Global Surveyor in 1997, Perseverance and Ingenuity in 2020. Other agencies joined in: Mars Express, Magellan, Tianwen-1, and more. Mars became routine. Venus became the planet you study from a distance. This wasn't just a cultural decision, it was an engineering decision. Mars is difficult, but it's workable. Its atmosphere is thin, its surface is cold but survivable for machines. Rovers can operate for years, even decades. Solar panels produce power, electronics can be protected, communication is manageable. Venus is different. Venus is what happens when a planet turns the environment into a weapon. The longest any lander has survived on the surface is just over 2 hours. So the argument became simple. Why spend so much effort on a place that kills your hardware quickly? But that question hides a mistake. Science isn't supposed to chase the easiest target. It's supposed to chase the most important questions. Venus holds one of the most important planetary questions we have. How do two almost twin planets end up with opposite fates? We know Venus wasn't always exactly like it is today, because the atmosphere still carries a fingerprint of loss. The key clue is heavier water, deuterium compared to normal hydrogen. On Venus, that ratio is about 150 times higher than Earth's. That suggests Venus once had far more water than it does now. How much water? Possibly enough to cover the planet in oceans. If oceans existed, liquid water had to be stable on the surface at some point. That means temperatures somewhere between 32 and 212 degrees Fahrenheit. It implies an atmosphere that behaved very differently. It implies clouds that were not sulfuric acid. So what flipped the switch? The leading explanation is runaway greenhouse warming. Venus is closer to the sun, so it receives more sunlight than Earth. But early in the solar system's history, the sun was dimmer, about 30% less luminous than it is today. So early Venus may have started in a much friendlier range. As the sun brightened, Venus warmed. Water evaporated. Water vapor traps heat, so warming triggers more evaporation, which triggers more warming. A feedback loop that doesn't stabilize. It accelerates. Eventually, the oceans would be gone. Ultraviolet light split water molecules. Hydrogen escaped to space. Oxygen reacted with rocks or other chemistry. Over hundreds of millions of years, Venus lost the water that could have regulated its climate. The carbon dioxide took over. On Earth, carbon dioxide is removed through weathering and plate tectonics, processes tied to liquid water. Without water, those things collapse. Volcanic outgassing can keep adding CO2, and there's no efficient way to remove it. Today, Venus's atmosphere is about 96% carbon dioxide, and the surface exceeds 842 degrees Fahrenheit, hot enough to melt lead, zinc, and tin. That's the broad outline, but the timeline and the details are still unresolved, and that's why Venus matters so much. Because this isn't only about our neighbor, it's about every rocky planet we're discovering around other stars. Exoplanet surveys have found thousands of planets. Many are Earth-sized or Venus-sized. Many orbit in the habitable zone where liquid water could, in theory, exist. But we can't see their surfaces. We measure mass, size, orbit. Sometimes we detect atmospheric composition, but usually only for the easiest cases. So the real question becomes, how do you tell an Earth-like world from a Venus-like world with limited data? Right now, we can't do that reliably. Because we don't fully understand which early conditions pushed Earth one way and Venus the other. Venus is the missing calibration point, and for decades we barely calibrated it. Then, in September of 2020, Venus forced a reset. A team reported Phosphine in the Venusian clouds based on observations from the James Clerk Maxwell Telescope in Hawaii and ALMA in Chile. They detected a spectral signature at 1.1 millimeter wavelength, consistent with phosphine. The reason it went viral is simple. On Earth, phosphine is produced almost exclusively by life, by anaerobic microbes in oxygen-poor environments. There are no known abiotic processes that produce it in large quantities on Earth. So the question appeared immediately: could there be life in Venus's clouds? The surface is lethal, but the cloud layer isn't the same environment. About 31 miles above the surface, the pressure can be similar to Earth's sea level, and temperatures can be relatively mild, roughly 68 to 86 degrees Fahrenheit. That doesn't make it friendly. Those droplets are still sulfuric acid, but it does make it a place where chemistry can behave differently than it does at the surface. Then came the whiplash. Reanalyses raised issues. Data processing, statistical uncertainty, and the possibility that sulfur dioxide could mimic part of the signal. Some groups argued there was no phosphine at all. Others argued the amount was smaller than first reported. Additional observations failed to detect phosphine. NASA's SOFIA saw nothing. The Infrared Telescope Facility in Hawaii saw nothing. Data from ESA's Venus Express, which orbited from 2006 to 2014, showed no signs of phosphine. The field split into camps, not because scientists enjoy drama, but because the atmosphere of Venus is complicated and our models are incomplete. Then in 2024, new observations from the James Clerk Maxwell Telescope reported phosphine again, with more data and improved analysis. The same team also reported preliminary evidence for ammonia. Ammonia is another puzzle. In Venus's oxidizing atmosphere, ammonia should be destroyed quickly by photochemistry, and ammonia has a second implication. Dissolved in sulfuric acid, it can act as a buffer, reducing acidity. That would make droplets less hostile, at least locally. None of this proves life, but it does prove something else. Venus's cloud chemistry is not behaving the way our simplest models predict. And there's only one way forward. Not arguments, not headlines, direct measurement. That's why the next phase of Venus exploration is so important. In June of 2021, NASA selected 2 discovery missions to Venus. After decades of relative neglect, Venus was suddenly back in focus. The first is Da Vinci Plus, a probe designed to descend through the atmosphere and measure composition all the way down. Noble gases, isotopes, trace compounds, the chemical story that can tell us when Venus lost its water. It will also target Alpha Regio, a tesserae region that may preserve evidence of a wetter past. Da Vinci Plus is designed to return a concentrated burst of data during descent. Then it reaches the surface and it fails. The second mission is Veritas, an orbiter with radar far more advanced than Magellan's. Veritas is currently planned to launch no earlier than 2031. NASA describes an aerobraking phase that reduces orbit via atmospheric drag. It drops apoapsis from nearly 20,000 miles to 250 miles. ESA is also returning. OnVision was selected in 2021 and adopted in 2024, targeting a launch in November of 2031. It is planned to reach Venus after a 15-month cruise, then use aerobraking before beginning its science orbit. This matters because Venus isn't a one-mission planet. It's a system problem. Geology, atmosphere, chemistry, and history all tied together. Venus is still one of the harshest environments we talk about exploring with hardware. At the surface, temperatures exceed 450 degrees Celsius, and the pressure is about 92 times Earth's. The atmosphere is corrosive, and sulfuric acid clouds attack materials above. Conventional electronics don't last. Silicon-based chips stop functioning around 150 degrees Celsius. Solder melts, circuit boards degrade, batteries fail, mechanical systems seize. The Soviet Venera landers survived through brute force engineering, thick pressure vessels, insulation, heat-absorbing materials. Even then, the longest survival time was about 2 hours. Modern technology offers a possible path forward, but it comes with trade-offs. Silicon carbide semiconductors can operate above 500 degrees Celsius and are used in extreme aerospace applications. NASA's Glenn Research Center has demonstrated silicon carbide integrated circuits functioning for more than 500 hours at 500 degrees Celsius. Some chips continued working in simulated Venus surface conditions for 60 days. That's roughly a 100-fold improvement over conventional electronics, enough to imagine surface missions lasting weeks or months instead of minutes. But the catch is complexity. These chips are still primitive compared to modern silicon. Their complexity is comparable to 1972-era computers. So you don't send a sophisticated rover, you send focused tools. simple instruments that answer high-value questions. The atmosphere has its own complications. It's less extreme than the surface, but it's dynamic. Venus rotates slowly, once every 243 Earth days, but winds at cloud level can reach 360 kilometers per hour. Any balloon or probe would be carried around the planet in just 4 days. That changes mission design. Instead of driving to targets, you drift with the wind. Instead of precise landing sites, you plan for moving observations. NASA has studied concepts for solar-powered aircraft that could cruise in the upper atmosphere indefinitely. The idea is to fly around 50 to 60 kilometers altitude where conditions are relatively benign. The bottleneck is cost. Venus missions often require custom solutions. Mars missions can build on decades of standardized hardware. That creates a cycle. Venus stays expensive, so missions stay rare. So the technology advances slowly, so Venus stays expensive. Breaking that cycle requires doing the opposite of what we did after Magellan. Not one mission, then silence. A sequence. A sustained program that makes Venus exploration less exotic and more routine. Because the deepest reason to study Venus isn't only Venus, it's Earth. And every rocky exoplanet we've ever labeled potentially habitable. Earth and Venus are nearly identical in size. Venus's diameter is 95% of Earth's. Its mass is 82%. Its density is almost the same. They formed from the same neighborhood of the solar nebula at roughly the same time, yet their fates diverged. One became a long-lived biosphere, the other became a warning label. This matters for Earth's far future too. Earth will eventually face a runaway greenhouse effect, not from human activity, but from the sun's long-term brightening. In about 1 billion years, solar output will rise enough to push Earth past a tipping point. Oceans evaporate, water vapor traps heat, hydrogen escapes. Earth becomes another Venus. Venus has already lived through its version of that transformation. If we want to understand where the boundaries of habitability really are, Venus is not optional. It's the most important failure case in our backyard. So the real mystery is not why Venus is hard. The mystery is why we tolerated decades of not knowing. After more than 30 years, that is finally changing. Not because Venus became friendly, but because we finally admitted it stayed important. And there is one more Venus mystery that keeps coming back, even in casual conversation. A mystery you can't ignore once you know it. Venus rotates differently from almost everything else in the inner solar system. As a practical step forward, understanding how common Earth really is and how common Venus might be. Not as a nostalgic return to a forgotten planet. That's why going back matters. And for a long time, we refused to calibrate it. It's a calibration point. Venus isn't just a cautionary tale. We're making that judgment without understanding the most important counterexample in our own backyard. Every time we label a distant rocky world potentially habitable because we can't explain Venus with confidence, whether the planet is still active today and how it got to this state in the first place. And that's how you finally answer the biggest Venus question. You learn which assumptions were wrong. You test models against reality. You refine hypotheses. With repeated missions, you don't just collect data, but because they can restart a feedback loop that Venus exploration never got to enjoy. Not because they'll deliver one headline and end the story. This is why the return missions matter. So what geologic activity happened without anyone recording it? What chemistry changed while we weren't watching? So the question becomes, what did we miss by waiting? But either way, they're the strongest candidate for preserving evidence of what Venus used to be. They may be ancient, or they may be the result of unusual processes we don't see on Earth. They hint that the planet's surface is layers of history we haven't learned to read yet. Even the tesserae are a kind of confession. Either way, Venus is telling us it's not finished. It's either being resurfaced or it has been resurfaced in the recent past. A planet with fewer than 1,000 craters isn't quietly aging, and it's why the crater count matters so much. It's a fossil record in the air. It's not trivia. That's why the heavy-water ratio matters so much. It controls what geology looks over long time. It controls what chemistry can exist. It controls the surface. On Venus, the atmosphere is the main character. On Mars, the atmosphere is thin enough that it's almost absent. It also gives you a different kind of lesson about atmospheres. A story that demands you get the physics right, or the mission ends fast. Venus gives you a hard story. A story you can revisit again and again with incremental improvements. Mars gives you a slow story. It forces you to learn what makes a planet flip from stable to unstable, because it forces you to study failure modes. And that's exactly why Venus is so valuable. It makes you choose between a quick, high-risk attempt or a long wait for better technology. It doesn't let you stretch a mission timeline until it feels safe. It doesn't let you park a rover and casually upgrade software for years. Venus doesn't let you do the comfortable version of planetary science. It was caused by a clash between curiosity and logistics. But the science wasn't caused by a lack of mysteries, so the silence after Magellan feels unnatural. It shows up in our calendars and in our myths. It shines brighter than any planet in the sky. Venus sits next door in orbital terms. It's because we've been close enough to take it for granted. And if you're wondering why Venus feels like a planet we should understand by now, it's about correcting a gap in our understanding of how rocky planets evolve. And that's why the return to Venus is not just about curiosity. Use targeted landers to validate what radar and remote sensing suggest. Use atmospheric probes to pin down chemistry and isotopes. Use orbiters to create global context. Build a chain of missions that feed into each other. Venus can't copy that exact path, but it can borrow the principle. Science questions became sharper because the platform became reliable. Operations became routine. Landing systems improved. Every Mars mission inherited knowledge from the previous one. Meanwhile, Mars did. The field never got the chance to iterate quickly. Magellan was a triumph, but it wasn't followed by a sustained sequence. Venus has been stuck in the curiosity category for too long, and reputation is how you separate pattern from accident. A program gives you repetition. A curiosity gives you a single mission and a single dataset. That's the difference between a curiosity and a program. It becomes a planet you can study systematically, and once you can do that, Venus stops being a one-shot planet. You can watch how the atmosphere moves and changes without your hardware dying instantly. You can monitor chemistry over time. You can place instruments there and keep them alive longer, because the cloud layer is where Venus transitions from totally impossible to conditionally measurable. That's also why the cloud layer matters so much, even if life never enters the story again. It was a reminder that we are operating with a missing ground truth, so the real value of the controversy wasn't a headline about life. Small errors in processing can produce big disagreements in interpretation. Signals can be confused by overlapping chemistry. Things that happen in one layer can be hidden by another, and Venus's atmosphere is layered and dynamic. It can't always tell you exactly where it forms, how stable it is, or what destroys it fastest. A telescope can suggest a molecule exists. Remote sensing is powerful, but it's not the same as sampling. That's why the debate became so messy so quickly. Uncertainties then multiply because we don't have enough direct measurements. Competing pathways. It offers chemistry, but Venus doesn't offer clean answers. Life or no life? Yes or no? Because the moment you hear possible biosignature, your mind wants a clean answer. It wasn't just the claim, it was the reaction. And the Phosphine episode is a perfect example of how Venus plays tricks on us. It becomes the story of what we choose to prioritize and what we postponed. It becomes institutional. It becomes historical. Because the answer stops being scientific. And once you treat it that way, the question, why did we never go back, becomes even sharper. A planet you track like a living system. It's a planet you monitor. Venus isn't a planet you visit, and that loops back to the core idea. The only way we'll be confident is by watching the planet over time, not just photographing it once. If Venus is still resurfacing today or volcanism is still active, new radar can reveal finer detail, subtle deformation, and possibly signs of active change. Magellan proved that radar can reveal global structure, and radar matters because it's the only way to read the surface through the clouds. Either way, tesserae are a reason Venus cannot stay on the sidelines. If they are not ancient, then Venus is doing something we don't see on Earth, and that is its own major discovery. If tesserae are ancient, they might preserve signatures of an era before the resurfacing reset the clock. There's a chance to read the planet's earlier chapters. They are not just weird terrain. That is why the tesserae are so important. You can find clues, but the planet is complicated enough that each clue creates new questions. You can measure chemistry, but you still need to connect it to geology. You can map the surface, but you still need composition. A single mission can't settle everything. Venus also punishes the hero mission mindset. And over decades, small preferences can turn into a huge bias in exploration. That matters more than it should because public attention can shape what gets funded over time. They are scientifically rich but emotionally colder. So the most honest images we have are radar maps and false color reconstructions. Venus hides its surface behind clouds, a place you can't emotionally stand on even if you've never been there. Rover tracks, rocks. Mars gives you landscapes. Venus is hard to love as a long-term project because it doesn't give you the kind of visuals people expect. There's also a human factor that doesn't show up in mission charts. That limbo is what is finally breaking. Too important to ignore, too hostile to treat casually. And without a complete story, Venus stays in a strange limbo. It did not give us a complete planetary story. Magellan gave us a surface map. The planet is too interconnected, and once you see Venus as one system, it becomes obvious why treating it as an occasional side mission was never going to work. Not as separate mysteries, but as one system. Surface, atmosphere, clouds, and interior. A full Venus program would connect those layers. They can tell us how much of the atmosphere is primordial, how much is outgassed, and how much has been chemically processed. They can move the story from we think to we measured, and that's why atmospheric probes matter. It can look for the subtle signatures of activity that a single snapshot would miss. An orbiter can map deformation, surface roughness, gravity fields, and changes over time. That's why orbiters matter. So it may release internal heat through different cycles. Venus does not appear to operate the same way. Earth has plate tectonics as a release valve. It is a clue about whether Venus dumps energy in rare catastrophic episodes or in steady long-term activity. It's a clue about internal heat and how the planet releases that heat. A resurfacing event is not just lava happened, it is also written in geology. It is written in what the atmosphere retained, what it lost, and what the surface absorbed. It is written in noble gases. The answer is written in atmospheric chemistry and isotopes. And right now, they are both still on the table in different forms. Those are radically different stories. Or did it stay stable for a long stretch only to tip later when conditions crossed a threshold? Did Venus lose its water early before life would have much chance to take hold? Not just what happened, but when it happened. And that is exactly why the big unknown is timeline. A planet can match Earth in bulk properties and still end up unrecognizable. But Venus proves that size is not destiny. When we talk about Earth-like exoplanets, we often mean size and distance from the star. Another reason Venus matters is that it sits on a knife edge of interpretation. You start by looking at the twin that went wrong. You start by looking at the closest near miss. You don't start by looking only at Earth. Because if you want to understand why Earth is special, a way of filling in a blind spot we've carried for decades, they're a correction. And that's why the return missions are more than a comeback story. It is one of the most important reference points we have for what a rocky planet can become. In other words, Venus is not a side quest, and it matters for how we interpret long-term planetary stability. It matters for how we interpret exoplanet habitable zones. That matters for how we interpret atmospheres in general. But because Venus is proof that a rocky planet can cross a threshold and become a different world. Not because Venus is a direct mirror of Earth today, it isn't. Venus also forces discipline in how we talk about climate and planetary futures. And when you finally do return to the surface, you return with a toolbox that has been tested in a Venus context, not just on paper. They let you iterate on instruments and methods while the hardware stays in conditions it can tolerate longer. They let you build confidence and competence without demanding long surface survival. That's also why orbiters and atmospheric platforms are so valuable early on. It's a way to make Venus missions less exotic and more repeatable. It's a set of proven components that can be adapted: pressure vessels, thermal management, communication, sampling tools. It's standardization. So the future of Venus isn't one heroic lander. And bespoke problems are expensive, risky, and easy to delay. Each mission concept tended to be treated as a bespoke problem. Venus never got that luxury. Teams reused designs, improved procedures, and built institutional memory. Each mission didn't start from scratch. Mars benefited from repetition. To make Venus exploration sustainable, you need something we accidentally built for Mars: a platform culture. We just didn't listen long enough. Because the truth is, Venus has been telling us for years that it deserves a permanent place in our exploration priorities. And familiarity is how science wins. It can become familiar. Venus is not going to become easy. It becomes mysterious in the productive way, the kind of mystery that drives better questions, better experiments, and better models. And once observation becomes a habit, Venus stops being mysterious in the frustrating way. It matters because it restarts observation as a habit, not as an exception. That's why the next era matters more than one set of results. If the surface is changing, it continues without a clock to measure it against. If the atmosphere is cycling through unexplained chemistry, it continues without samples. If volcanism is still active, it continues without witnesses. Meanwhile, the planet keeps doing whatever it is doing. Because we kept waiting for the perfect mission architecture, not because we stopped caring. That's how important worlds get ignored. And when missions have to be definitive, they get delayed. That makes every mission feel like it has to be definitive. On Venus, each step is expensive, and the environment tries to erase your progress quickly. You can return to a crater, climb a hill, sample new rocks, and build a narrative step by step. On Mars, each new rover extends the previous story. Part of it is that Venus doesn't reward incremental exploration in the way Mars does. Why did Venus, of all planets, become the one we treated like a problem to postpone? And this brings us back to the emotional mystery. That's the hidden payoff that makes Venus worth the difficulty. It will reshape how we interpret Earth-sized planets around other stars. The impact won't be limited to Venus. So when the next generation of missions returns more detailed radar maps, deeper atmospheric chemistry, and better constraints on history, it updates our expectations for a whole class of planets. It doesn't just describe Venus, and it's why every new data point from Venus has outsized value. It's the nearest example of how thin the line can be between stable and unstable. That's why Venus is the planet that keeps showing up in serious discussions about rocky worlds. Over long durations, small differences become different worlds. A different rate of internal heat release, a slightly different early atmosphere, a little less water, a little more sunlight. In planetary science, that difference often comes down to small initial conditions amplified over time. Two objects can share the same category and still be fundamentally different in outcomes. Venus also teaches a lesson about twins. They are the marks of a world that still has leverage over our understanding. Those are not marks of a solved world. We know the atmosphere is extreme, but we still catch it behaving in ways our models struggle to explain. We know the planet lost water, but we don't know exactly when the loss became irreversible. We know the planet looks young, but we don't know how it renews itself. But not enough to be certain. We know enough to be disturbed. And if you want the simplest possible summary of the Venus problem, it is this. Speaking of planetary mysteries, there's something strange about Mercury and Venus. They are the only planets without moons. Jupiter has 92. Saturn has over 200. But these two, 0. Watch our video on why Mercury and Venus don't have moons to discover what the sun's gravity does to everything nearby.